Hello everybody, I woke up this morning and my voice sounded like this. So we are going to do our best here. I promise I am usually a little bit better than this. It was a 9-hour flight, so. My name is Liz Frost. I am a SRE4 on PagerDuty's core infrastructure team, which is honestly basically the service mesh team at this point. Here are the two mandatory pictures of my containerized cats. One quick note before I get started. I pronounce the word Kubernetes differently than everybody else. You have not heard it wrong. I am incorrect. But I also worked with Joe Beta and one of the other Kubernetes co-founders for 2 years, and they never corrected me, which I have taken as a sort of tacit acceptance of my pronunciation. So I've got 3 sections for you. 1, what to know before you go. 2, how we actually did it. And then 3, all the little miscellaneous bits that didn't quite fit in anywhere else. So what we have at PagerDuty are a lot of different things that made this process difficult. Number 1, we have a service discovery mechanism in console. We use Kubernetes now, but until very recently it was Nomad. And that means that our organization is already burned out from a quite long migration process. We use a lot of Elixir. Elixir is a very great language, but it's not a very popular one, which means that there are not a lot of tools that exist in other languages. And if it was only Elixir, that would probably also be fine, but we also have a whole bunch of other ones. We have what we call opinionated wrapper libraries, or OWLs, which provide some places to instrument things, but mostly just provide a lot of layers of indirection. And then finally, as far as this process is concerned, we have a lot of small rocks and one very big one that I will get to soon. So this is from our deck, the breakdown of all of the different apps that we need to migrate. And one of the problems is there are too many languages. There are too many implementations of those languages. And by this I mean specifically, if you want rate limiting, odds are good your team has written a bespoke rate limiting mechanism and nobody else can use it. You want circuit breaking, you probably wrote it yourself. That means a lot of teams either spend time they don't need to spend maintaining these resources, or they just don't bother writing them at all. And on top of that, my company is partially American, which means we care about FedRAMP, which is a very onerous compliance thing, and it requires encryption in transit for basically everything. So with all of those things, we have languages that are different. We have a bunch of traffic management needs. We have compliance issues. Obviously, we need a service mesh. Now, getting into this first, the pros we knew kind of right off the bat. Increased visibility, that means universal metrics that look the same everywhere, logs that look the same everywhere. That's great. Security is mostly going to be that encryption in transit that I mentioned earlier. But the traffic features are the really interesting part. That includes things like automatic retries, automatic canaries, circuit breakers, all of that kind of thing. And we knew about the complexity. We knew that it would be complicated. We didn't know quite how complicated. We knew that there would be some amount of latency. We knew that there was going to be a lot of resource usage because all of those sidecars have to run somewhere. And by running somewhere, they take up resources that would otherwise be used by our applications. And most importantly, we knew there would be some degree of learning curve. We were really hoping for a curve that looked like this. As we get more and more things onto our mesh, we would gain more and more value from the way those things interacted with each other. What we actually got was something more like this. And I will tell you why. Because on day 1 of the service mesh, you don't get any of those security features, and you don't get any of those traffic features. Now the good news is the metrics work great. Whereas before, every application would have its own bespoke metrics names, and maybe you did 5xx, but somebody else did separate metrics for 500, 501, 502. Almost impossible to correlate how these things worked. And now we can just see a big, this is the amount of traffic passing through the mesh over time, which has been super handy. And it is a nice fancy graph that goes up that helps us measure our progress. Security, it's a little less rosy. Obviously, when you first start putting 1 or 2 applications on the mesh, you can't enforce that all of these applications use encryption to talk to each other, because most of them just wouldn't work. And no enforcement means there's no validation. You can't say, oh, I know that this is a connection that is secured, so I don't have to do any of my normal validation on it, which is what we were hoping to do. So you have the overhead of those fancy HTTPS connections everywhere, maybe, but also you don't have any of the nice things that come with that, like being able to trust all of your incoming connections. And from most perspectives, encrypting 2 out of 3 hops is basically no encryption whatsoever. Your compliance auditor is not going to let you get away with, okay, but almost every time we have this encrypted. And the traffic features, that was even more complicated. I'm going to give a brief detour through how some networking works in Kubernetes. This is a Kubernetes service object. The code isn't actually that important, but it has a selector which says, I want a application that looks like, that matches these labels, and I'm going to route traffic through it. And this is probably how you think this works. It's certainly how I think it works, and I think for a while it actually was how it works. There's a downstream, something called kubeproxy in the way, and it routes to upstreams. But it turns out kubeproxy isn't a proxy anymore. It's something more like this. There is not actually any cluster IP assigned to an interface. There is no container running somewhere that is listening on that address. There is no proxy. What is actually happening here is that kubeproxy is setting up a IP tables rule that matches traffic to that cluster IP. IP tables then rewrites that cluster IP to be a random pod IP. And if you look at the IP tables output, you can literally see it's 50% chance of this, and then 33% chance of this. All of this happens inside of the host. Now, why did I explain this to you? This is a virtual service. I would describe perhaps the previous service as also virtual, but that's what the sort of layer on top of services is called in Istio. And it is basically, at this point, a pretty thin wrapper around the service object that I had previously. But I did add one thing, which is that I wanted you to retry 3 times. And again, the way that you probably would think about this is that there is a downstream, there's this sort of virtual service object, and then there is an upstream. But let's take a closer look at this. The downstream is in one namespace, we will say, and the upstream is in a different namespace. And that's important because it means the virtual service is sort of logically associated with the upstream. It is mostly concerned with the traffic to the upstream. But, and this is very important, all of that implementation, all of the actual logic from that virtual service That is not implemented in the upstream sidecar at all. It all flows into the downstream sidecar in a completely different namespace. So if that downstream sidecar doesn't exist, if that downstream isn't on the mesh, well, it's basically going to completely ignore that traffic. It is going to take all of that information and say, well, I have never heard of this. The sidecar on the upstream is really just used for metrics and terminating mTLS. None of those fancy L7 features, traffic shaping, any of that stuff, none of that exists. So if we only have the downstream on the mesh, well, then we don't have that virtual service, so there's nothing actually interesting being done there. And if we actually had the virtual service, the sidecar, and the upstream, honestly, nobody really knows what would happen. Our consultant certainly didn't. People don't really do this because why would you bother having a virtual service for something that didn't even know the mesh existed yet? This is all happening downstream, but it's all configured upstream. And that is not just a technical problem. Because previously, all of the configuration for these things like retries and circuit breakers, those were configured by the client. And now they are configured by the upstream service. And that means potentially it is now a different team that controls these interfaces. So in addition to having to do all of the work of getting your information, your application onto the service mesh, now you also can't do the thing we promised you could do, which was get rid of all of your custom implementations, until all of your upstreams are also on the mesh, and you have coordinated this handover carefully with them. And you have to coordinate carefully because if you have two sets of retries, what you are basically going to see is that a request comes in, it fails, but it doesn't fail immediately because that request is passed to the service mesh, which tries 3 times. Those 3 times of retries are completely transparent to the client, so it thinks only 1 failure has occurred. So it does it again, and then it fails 3 times in the mesh. And the upshot is you have a n² problem, where you thought you were getting 3 retries, and you were actually getting 9. And you can imagine if this was 5, for example, it's even worse. So you have to be very careful about how you hand this configuration from off the mesh onto the mesh. And there's a similar problem with canaries. Now we use Argo for our CI/CD, but I think this applies to most things. The way canaries work with Argo right now is it's basically round robin the number of pods. So if I have one pod that I've called my canary and one pod that I've called stable, we're going to get 50% traffic to both of those. If I wanted to have, say, 10% of my traffic go to the canary and 90% of it go to stable, the only way to do that is to have 1 canary pod and 9 stable pods. And that's not really what you want. So we have this promised land of when the downstreams are on the mesh, we can have 10% of requests go to 1 pod and 90% go to the other pod. And all of that stuff will be nicely enforced and handled. But I think you know where this might be going. What happens if one of them is on the mesh and one of them isn't? Then the one that is on the mesh is going to send 10% of its traffic, but the other one is going to continue doing the round robin thing. And that basically means it's impossible to reason about how much traffic you are going to get, because it depends on not only how many downstreams you have, but whether those have gone through the mesh enrollment process and the number of stable pods that you have at any given moment. So the upshot is that both the canaries and the retries thing are unreliable until all of your downstreams and all of your upstreams are on the mesh. So, okay, I put this section first, not because it was the first thing that happened, but because if you wanted to, if you got through this part of the talk and you were just like, wow, this service mesh thing sounds horrible, I don't need to deal with it, excellent. But we had to learn these lessons the hard way, so let me tell you a little bit about how we migrated. Pardon me. Now, this is obviously PagerDuty's most critical service, Pony API and PonyDB. And these actually do run in production because we needed some example applications to test out the mesh. But I'm basically just going to use this as a series of domain names for you. So this is how it works right now. We have a PonyDB, that's our upstream, that boots up, and we have a dedicated sidecar that says, okay, this is healthy. I will register my pod IP with console. And then the downstream, Pony API, says, okay, where is ponydb.svc.console? And it will get one of those pod IPs back. Pretty simple discovery mechanism. Now, how does Istio traffic usually get routed? There are a couple of different ways that you can route traffic. You can route to the full name.namespace.svc.cluster.local. You can route to name.namespace. If you're in the same namespace, you can route to just name. And this one is pretty interesting. If you send traffic specifically to the cluster IP for a service, Kubernetes or Istio knows about that and will route it all correctly. So how do we do this migration process? Well, one thing that we could try is just sticking that .console host inside of Istio. It would be pretty weird to have a .service.console address and not have console anymore. But we already have a lot of Kubernetes variables namespaced with nomad underscore, so it's not exactly a weird thing to do. And if it saved us that migration, that would be great. And that would have worked. We could simply add that. But unfortunately, those owls that I told you about at the very beginning, they are very wise and do not work exactly how we expect. You probably can't see all of this, but basically, because DNS is so unreliable, there is a process running in all of our Elixir services that is regularly polling the console API. It is getting those IPs, and then it is randomly selecting one of those IPs at runtime to send all of the traffic to that IP. And importantly, it is sending the traffic to that IP directly, which means there is no host header that says .service.console. There's nothing to match on. It's just going directly to the pod IP. And Istio cannot route to the pod IPs. It doesn't know about them. Istio can route to almost anything else, but if there's no host header and no pod and no cluster IP, it doesn't know where this is supposed to go, and so it just won't get routed properly. And it needs to know where it's going to go because the process of having a sidecar strips that information about the target IP out of the entire thing. So it won't know where to route the traffic, and even if it does, it won't be able to do any Istio stuff to it because it can't tell where that traffic is going. So in the end, we ended up with a two-phase migration, where the first phase was we would switch everything from these bespoke console providers to just name.namespace.svc.cluster.local. And by doing that, I mean also all of these services hadn't been touched in a while, so we had to update the dependencies, change the wrapper libraries. We had moved to a new upstream package provider in the meantime, so we had to do that migration. We had to replace all of the names because console names aren't namespaced, so the names are just a little bit different. And this list on the right-hand side, is all of the different things that we had to do. And it's 2025, as Liz said. Did we use an AI? We used SED, which is the original AI. We used what we call a away team model, which is basically where my team does this for the entire company, because if we asked the entire company to do it, they probably wouldn't. And basically, we divide up everything by language. So there was one team that just worked on those Elixir languages, and one team that worked on all of the special stuff, and one team that worked on the big rock, which we will get to very soon. But this was helpful because it concentrated all of the experience of doing this migration in our team. That's how we got that fancy SED thing that did 90% of the work that we needed to do, because we were constantly iterating on this. And all of this means that we got quite good at it. There was like a month or two where I came in every day and I would just crank through 2 or 3 of these. And there were a couple of people on my team. It's embarrassingly parallelizable work, so a lot of people can do it. And perhaps most importantly, by not forcing the entire rest of the company to do this, we preserve our team's reputation as not simply forcing you to do a whole bunch of work for no reason. So we would send these API changes over. We would ask very, very nicely for the rest of the company to test them thoroughly. And then after that was done, we would move on to phase 2. And phase 2 was actually very simple because we have Helm charts for all of these services. And that means that instead of having to have a large, complicated mesh onboarding procedure, in your custom PagerDuty branded Helm chart, you can just say mesh enabled true. And that actually concentrated more of our expertise. Because in addition to just saying enabled true or false, we could give you things like access logs. We could give you things like maximum request header sizes. The access logs, they look like this. This is what the Helm is going to spit out when you turn that on. And it's not that big of a deal. Disabled, false, providers, full. That's all configured upstream. But something like max header size, it looks a little bit more like this. And I will get to these kinds of configuration snippets in a future section, but suffice it to say, we did not want people to be copy-pasting these from wherever to wherever else. So having those Helm charts sort of abstract this away was super helpful. And then basically we just did regular project management to it. We got specific slots from teams where they would have dedicated availability to us. We made sure that their migrations were ready before those slots, and we just kind of burned through it. I'm pretty proud of the slope of this graph. You can definitely see where some of us went on winter holidays in there and some other time off, but that's a pretty good slope. But one of the things you will notice is that it doesn't get to 0. And that's not just because I cut it off in April, but that's because in addition to all of these small little microservices, we also have one very big rock. I think there are probably a lot of companies that have a whole bunch of very fancy microservices, and then one application called like web or main or something that is a Rails application that has existed since the founding of your company and still contains 80% of your business. So we have one of these, and we started doing our regular process. We went through, we ran our fancy sed script, and we got this, which is a big ol' spike in 500s when we finally got around to trying to put this on the mesh. And importantly, they are all timeouts. And this is important because Rails, at least as we run it, is synchronous, which means if I have a 44-second timeout, that is almost a minute that one of my workers is completely unavailable. Asynchronous frameworks, they would be blocking, but that worker would still be doing stuff waiting for traffic to come through. But with a synchronous framework like Rails, if you have 30 workers and 5 of them are waiting for these timeouts, you actually only have 25. And that meant that even though this was a relatively small number of requests that were failing, they were tying up a very disproportionate amount of our resources while they were happening. We tried a bunch of different things to fix this. We tried, for example, putting both web as the client and the microservice upstreams on the mesh to see if if having both of those halves be in the same place would help. Not really. We built out a isolated Kubernetes fleet that didn't have anything running on it in case it was some kind of resource or like noisy neighbor issue. Not really. We tried adding more memory and more CPU usage. That didn't work. And most importantly, what didn't work was any reproduction of this anywhere except our production environment. We think the problem is probably kube proxy or IP tables or something like that, but we're not 100% sure. Half the reason that this slide is in here is that I'm hoping there's somebody with Istio experience who has a great idea for us. But until then, there's a couple things we can try. There's different modes to run Istio in. There's different modes to run kube proxy in. But one thing I do want to talk to you about is combinatorics, which is basically the amount of information every sidecar gets grows very quickly with the number of services that it knows about. Now, if you have 2 pods, this is pretty straightforward. Like, each pod needs to roughly know about where the other pods are because they're probably in services. And with 2 pods like this, like you would have on a little example cluster, that's not a lot. If I move it to 6 applications, well, suddenly the number of arrows is getting up very, very quickly. And if you have 4,000 pods like we do, it looks, well, I don't know what it looks like, but it doesn't look good. And we had not taken the step of saying, okay, this application only needs to know about this, 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 and this upstream, which meant every application was gaining the routing information for every single other application that was on our mesh. We don't know for sure that this is the problem, but it is certainly causing a lot of resource usage, and it is probably something we are going to need to fix. We didn't want to fix it ahead of time because we were really hoping that having everything on the mesh would give us one place to go to see what our upstreams were. But unfortunately, we have ended up in a little bit of a catch-22 here. So here are my random gotchas. One, something that I probably could have figured out ahead of time, not everything is HTTP. And in particular, this was a HTTPS terminated request, but, well, not HTTPS, but it was TLS. And this is sort of how we think about the Envoy proxy. There's just like a thing in the middle, and it just sends traffic from one side to the other. But if you've seen me put diagrams on here before, and you know that this is not the entire story. This is actually how the transparent proxy works. This is a diagram from Jimmy Song's excellent blog. And in fact, it is kind of tunneling through, but it still has to interpret all of that TLS. It still has to go through Envoy. It's not literally transparent. And so at some point, we ended up with a random SSL error. And the solution to that was switching from one library that had an old version of libcurl to another library that had a newer version of NetHTTP. Why did that work? I don't know. But we finished the efforts to migrate faster than we finished the efforts to figure out what was wrong, and so we just sort of took the win and went with it. One of the things we were very excited about was rate limiting, and it turns out that Istio doesn't actually have any native rate limiting support. It delegates all of this to Envoy, and dealing with Envoy configuration is very difficult. Another example with that, we had some applications that had very large headers. I put this cat in here because how often do you get to see code 431? You have to write these complicated things called Envoy filter configs. And where do you get this like arcane invocation? Well, obviously you go to the Istio GitHub repo and hope that somebody else has figured it out. Because if you look at the configuration that this is modifying, it is very long. It is several thousand lines of JSON that is constantly being upgraded. So this is me trying to figure out exactly where this Envoy filter was going to end up. And you can see that there are listeners matches one thing in that configuration, and then there's dynamic listeners, and there's virtual inbound. All of this stuff, I don't even remember what it means anymore. I just found this in my shell history. And of course, randomly doing these sort of low-level patching on Envoy could never cause any problems, right? These are not like nice errors that get logged and spit out some sort of, uh-oh, there was a failure. No, this is a hard crash of the Istio daemon that was happening every single time. And eventually we figured out that we had slightly underspecified where this patch was going, and so it was ending up with something out of bounds. But this is, when you move beyond the sort of like abstraction that Istio provides, you have to be very, very careful because there are very few guardrails left. A couple other problems that exist. You can auto-scale containers, obviously, but as more and more applications made their way onto the mesh, those sidecars, for the combinatorics reason I gave earlier, require more and more resources. And we don't have a way to auto-scale the size of those sidecars specifically. So what we do have are a bunch of alerts that we set up when we install these Istio things, and then those teams get an alert that says, please follow this runbook. And then they come to us to ask us what to do, and we tell them to please follow this runbook. And then usually we sort it out. It's not that big a deal, but it is a sort of ongoing issue. And we could just give an enormous allocation to every single one, but then that is a whole lot of compute that won't be used that we have to pay for. One other little thing that we had, when we first started doing this migration, if you wanted to have a cron job or a job, which is a process that runs and then terminates, and you wanted that to be on the service mesh, you had to come up with some fancy way to tell the service mesh to end, because otherwise, the mesh container would keep running, and Kubernetes would say, well, it's still running, so I can't terminate it. But fortunately, there is now native support for sidecars in Kubernetes 129, which isn't even that new anymore. It is stable, and it is now the default in Istio, so none of you have to worry about it. I just wanted to complain about it because it made my life very miserable for a little bit. In conclusion, this is roughly where I'd say we are on the chart. We are getting close. You can tell that adoption is like kind of asymptotic. Like we're getting close, but we're not quite there yet. We have some of this value, but not all of it. And, you know, we're getting there. I don't know what the time axis looks like. That could be next week. That could be 6 months from now. But the only way out is through. I was Liz Frost. Thank you all very much for coming.